everyone. Yesterday, I briefly introduced to you the word piecewise. A piecewise function, by definition, is the piecing together of two functions at a particular point. So what we're going to do for this first example is we are going to find the data for one side of the piecewise. We're going to find the data for the other side of the piecewise, and then we're going to put them together. So step one says make a table of values for the function y equals 2x minus 1 using all of these points. So if 2x minus 1 is plugged in at -3, 2 times -3 is -6. -6 minus 1 is -7. -2 times 2 is -4 minus 1 is -5. So since our slope is positive 2, my y values are going up 2 for every x we go over 1. So then we are going to do the same thing, but now I'm going to make a table of values for the next linear equation. So this linear equation is -x plus 3. So I'm going to start at 0 and find all of the values for this. So that's 3, 2, 1, 0, -1, -2, and -3. Again, my slope is -1 and my y-intercept is 3. So starting at 3, we're going down by 1 as we go over by 1. What we're going to do now is on the first graph on our paper that we ripped out, we are going to draw in 2 vertical lines. One vertical line is going to be drawn in at -2. No. The next vertical line is going to be drawn in at x equals 1. And what I want you to do is to graph the points from the first table on this line that you drew in the vertical line. So graph the point -3, -7, -2, 5, -5, sorry, -1, -3, 0, -1, 1, 1, and so on. Y equals 2x minus 1 is a linear function. So you would connect the lines. So in part 1, the graph y equals 2x minus 1 looks like this graph right here as a whole. This graph right here has a domain and range of all reals currently. So the pink line is a domain and range of all reals. What we're going to do now is cut out our graph on the 2 vertical lines. Make sure you understand the top and bottom of your graph. Yeah. Step 3 on the directions. What you want to do is then take that graph you just cut out and place it where it would belong at the bottom of your paper. Bottom of your paper, like I did up on the board. Yeah. Did we keep the bottom and top on? You keep it almost exactly like I did. Then you're going, so mine are walked away and taking it. You're gonna line up the X and Y axis so that their top and bottom of your graph are the same as when you cut it out. Did you want to blink brackets or do this with us? No, I didn't do it. Yeah. I just meant even right now. Okay. Oh, put this up and put it at the bottom of that page. Okay. It's probably just the way that Microsoft on the top or bottom of the piece of paper. I brought it to you. Turn around and ask me for a piece. I just put mine at the top to hold the graph in place. No. Fantastic. I'm going to give you a second piece for the next graph so you can tape the bottom down. All right. So now on the second graph at the top of that page, so right here, after you've cut out the first graph, so now that one's gone, you're going to go over to this graph. And we are going to graph the second equation. So in this one, you're going to graph y equals negative x plus 3. So you're going to plot the points you got in part 2. So 0, 3, 1, 2, 2, 1, 3, 0, 4, negative 1, 5, negative 2, and 6, negative 3. Connect your lines. So in the second table, on the second graph, using that table, you graph the line y equals negative x plus 3. Now what we're going to do is draw in a vertical line at x equals 1. And a vertical line at x equals 5. And then just like we did in step 3, we're going to cut out this part of our line. On those two lines again. And then what we're going to do is line them up. Yeah, I see that. It's okay. Yeah. I wonder if I measured them to go down and not over. Yeah, I lined up the y-axis and it was fine. It's just the bottom axis is a little short. And then what I want you to notice is, do the y values match at x equals 1? Yes. No. No. So what happens is at x equals 1, the left graph is at 1, and the right graph is at 2. So these do not match up. So if we talk about continuity, are they continuous? No. So then, for whatever reason, the computer program, and once again, so I get the printing in different rooms, it changed all of the stuff at the bottom. So we're going to rewrite that as a piecewise function that makes sense. Okay. So a piecewise function is the piecing together of two functions. So f of x in this case is equal to the pink and the green. So the pink is 2x minus 1. And the green is negative x plus 3. If you think about the pink function, we started it at negative 2 and ended at 1. So its domain is negative 2 to 1. And we're going to talk tomorrow about whether that negative 2 and 1 are included, depending on if the points on the graph are open or closed. So if I told you this point here is closed, then this would be included. So it would have an equal on our graph. In example number 2, whatever it's called. In example number 2, we cut our lines at 1 and 5. So if I said it x equals 5, it was included or a closed circle, then my graph would go from 1 to 5. The equal tells me it's including 5. So the domain of this f of x we've created, and let's say the green graph also includes 1. Our domain would be negative 2 to 5. And my range would be the highest to lowest or lowest to highest. So the lowest point is on the pink graph, which is at negative 5. And because it was closed at negative 2, it includes negative 5. And then it goes to the green graph at 1, 2, and includes 2 because 2 is included. So the range is negative 5 to 2. This pink point here is like an open circle. So does this graph pass the vertical line test? Yes. Yes, it does. For every x, there is only one y. Because at x equals 1 on the pink graph, it's not included. Therefore, it passes the vertical line test. So this is a function. Is it 1-to-1? No. Does it pass the horizontal line test? No. What? Because this point is closed and this point is open. So at x equals 1 is the only point at which we have an overlapping of the two functions, because the pink lives from -2 to 1 and the green lives from 1 to 5. But the pink graph does not include 1. So like if you were graphing this on a number line, it would be a closed circle at -2, but an open circle at 1. So is 1 included in your solutions? So over here, because we graphed a line using that inequality idea, the 1 is not included in my solutions. Therefore, it passes the vertical line test. So what we're going to do is complete the next set of problems on the back. I'm going to have you fix this problem. So this is really just that bracket. And these L's are just less thans. So these inequalities tell you where you're going to cut your graph. Now, if you don't want to do the cutting and the taping, you can just draw the graph from -2 to 2 of 3x. So this table goes with 3x. This table goes with 6. And this table goes with -x plus 10. So take a minute and complete your tables for these 3 graphs right now. So don't worry about the graphing part. Complete your tables. Oh, here you go. Okay, so here are your tables and here are your graphs. Does anybody need help with any of those 3 things? Now I'm going to pose the question to you. Where do I draw my vertical lines for the graphs? So, go ahead, Addison. Where am I going to draw the vertical line for 3x? Correct. So in this graph, because I'm going to use the inequality that sets its values, I would draw in a line at -2 and a +2. And that's where I cut. How about on the second graph for 6? Lucas? Perfect. Okay, and then on my last graph, grab Lucas. Perfect. Yeah. So right now, they're all where we drew in our lines, they're considered open because the inequalities are open. And then the in between the inequalities are filled in because it's kind of like our old inequality that looks like this. So if it was an endpoint and it was equal to, it was closed. And if it was endpoint and it was less than, it was open. And then everything in between is included. So now it's the same. So we're basically taking this segment right here of the graph, but applying a slope and a y-intercept to it.
Yeah. So like this one, I would color in, I would fill in all these bubbles because they're inside of it.
Yes. Okay. Yes. Make sure you don't tape your graphs upside down. I'm coming. I want to just set mine up for you. Yes, it does. A little bit. That's what I thought. Okay. Correct. And you're all filled in. Okay, guys, so then your assignment for tonight is to do formal and the math card activity. So you can do that on your own now. And you can take time so you can grab it and pencil. Or you can do it every day and just grab it on the line. Again, the big thing, like when I get asked questions, all of these dots are closed between them. These dots are closed. This is closed. The endpoints would be open because none of the inequalities are equal to. The endpoints would be open because none of the inequalities are equal to. 6 to 2. So if you do the next one, the tape's up here. You can grab yourself a piece of tape and put your scissors away. If you just grab it on your paper without doing the cutting, that's fine also. Yes. Yes. Correct. Just make sure your graph has a beginning and an end that match the endpoints of the inequality. So, like, don't draw this bottom graph less than 0 or greater than 3. Since you're not cutting, like here, you can see for like the orange graph that we cut out, it extended beyond what we needed. Same with like the 6.
Well, see, the first graph on here is less than 0, so we put everything greater.
Yep, less than 0. Yeah, why would you do greater than? It ends at 0.